So today we're going to look at our nth root functions. When we're talking about an nth root, basically what we're talking about is all other types of roots, including our square roots, but these could also be third roots and fourth roots. So we're not just dealing with strictly square roots anymore. So let's look a little bit at what these might look like. So for an nth root, in general, this is the inverse of raising to the power of n. So looking over here, the little n inside is called our index. The root is called our radical. And whatever's on the inside is called our radicand. This would be the nth root of 81. Whenever we're looking for a principal root, this is the non-negative when an index is even. Because if we think about it, like with our square roots, 2 times 2 gives us 4. So if I had the square root of 4, it would be 2. However, negative 2 times negative 2 is also 4. So if I took the square root of 4, we could technically say that it's 2 or negative 2. However, when we're talking about even roots, we want to be dealing in our real numbers. So we're going to stick with our principal roots, which will be those positive roots. Now, looking at some examples, if I have x to the third equals 64, well, I know that 4 times 4 times 4 equals 64. So we could say that the third root of 64 is 4. Likewise, 5 multiplied together 4 times is 625. So we could say that the fourth root of 625 is 5. 2 multiplied together 5 times is 32. So we could say the fifth root of 32 is 2. And in general, basically anytime that I'm trying to take the nth root of something, I'm looking at what multiplied together n times equals whatever is underneath that radical. Now we do have a few root properties. So if we're looking at the nth root of a, okay, and we have two basically different types of situations that we could be in. The first one would be that n is even, and the second being that n is odd. So I can take a square root, a fourth root, and so forth, and all of those would be an index that's an even number. And then obviously I have a third root, a fifth root, a seventh root, all of my odd numbers. So if my radicand, or in this case a, is positive and I have an even root, I will have 1 real root. And it's going to be positive. This would also be true if my n is odd. So we would still have 1 real root and it's going to be positive. Now what changes is when the stuff on the inside, or remember what's called our radicand, is negative. So if our radicand is negative and we have an even root, there will be 0 or no real roots. So we could say that it does not exist or it is undefined. However, if our n is odd, we will still have 1 real root, but this time it'll be negative. And the nice thing about our last one is that anytime we take any root of 0, whether it is even or odd, our answer is always just going to be 0. So let's look at some examples. So here, it asks us to simplify. We have the plus or minus, and so if it specifies if we're wanting the positive or the negative, or in this case both, then we'll just leave it out there. Again, if it doesn't specify, then we're assuming that we're finding the principal root. So in order to simplify, remember that we said the radical on the outside is the inverse of raising it to the same power as our index. Well, if you notice on both A and B and D, there's not an index there. So in general, if there is no index, it is an understood two. Or basically I have a square root. Since our square root is the most common root, basically they just said, okay, if I don't see any index there, then it's understood to be a square root. So in this case, we have a square root. So the way that we want to go about reducing these is that I want to try and rewrite everything on the inside of my radical to whatever power my index is. So in this case, my index is 2. So I want to rewrite everything as a power of 2 on the inside of my radical. So hopefully we can notice that I know that 16 is going to be 4 squared. And then also we could rewrite y to the 4th as y squared squared. And the reason that we want to do this is because, remembering back to our exponent properties, if I have two things and I raise them to a power, I can think of it like distributing my power. But that means that this also works backwards. So if I have two different things that are raised to the same power, I can combine them in one set of parentheses and say that they're all raised to that power. And the reason we want to do that is because, remember, we said that a radical and our exponent of whatever our index is are inverses of one another. So we're just going to end up with plus or minus 4y squared. And that would be our answer. And our next one, they specify for us that they want the -1, which is fine. And again, we don't have a radical here, so it's an understood 2. So again, I want to try and rewrite the stuff to a second power. Well, hopefully we notice that we have an exponent of 8. And one of our other properties tells us that whenever I raise a power to another power, we multiply those powers. So I know that if I were to separate this out into x squared minus 6 to the 4th, all raised to the 2nd, then when I wanted to simplify that, I would do 4 times 2, which would give me 8. And the reason we want to rewrite it like that, again, is because now that I have a second power on the inside, it's going to reduce. And so we're just left with a negative x squared minus 6 to the 4th power. And that would be my answer. Now, on this next one, we have a 5th root, which again, we're going to use this same process. The only difference now is that we're looking to write things to 5th powers instead of 2nd powers. Now, most of us aren't going to know our 5th of like raising things to the 5th powers like we do our squareds or even sometimes our thirds. So most of the time we're just going to have to guesstimate, right? Well, if I say 243, I'm assuming that that's not going to be 2 to the 5th because it's an odd number. And if I plug that into my calculator, 2 to the 5th is 32. Well, then let's go ahead and go to a 3. So I would say 3 to the 5th. Well, look at that. It is indeed 243. So I know that I can rewrite 243 as 3 to the 5th power. And again, we want to do a similar thing with our A and our B. So remember that if I raise a power to another power, we can multiply those powers. So 20, we could separate into 4 times 5. And we want that 5 to be the outside number because, again, remember that that's what we're trying to reduce. Now, on my second one, we have b to the 25th, which would be 5 times 5. Well, since they're the same thing, it doesn't matter which one we write. And then now, because all of my exponents are the same, we can rewrite this as 1 parentheses to the exponent of 5. And now, because my index of my radical and my exponent are the same, they will reduce with one another. So we know that we're left with 3a to the 4th, b to the 5th. And then on this last one, notice again we have a square root. But hopefully we notice that we have a negative 16 there. The problem with that is because it's a negative 16, basically we're looking for what two numbers multiply together to give us negative 16. Well, if you said 4, well, 4 times 4 gives, let's say, positive 16. And if you said negative 4, well, negative 4 times negative 4 is also a positive 16. So there's not a number that we could multiply by itself, basically, and end up with that correct negative in there. So again, remember, if my root is even and I have a negative underneath it, there is no real root. However, let's think about if I had something like the third root of negative 64x to the third. Well, notice that I have a negative, but this time my root index is a 3. Well, 3 is an odd number. Well, if I go back and I look, okay, well, 2 to the third is 8. 3 to the third is 27. 4 to the third is 64. So that gives me that correct number. Well, if I think about it, I'm talking about multiplying negative 4 together 3 times. So negative 4 times negative 4 would give me a positive 16. And then we would still be left with 1 negative 4. Well, now notice 16, which is now positive, times a negative 4 gives me a negative 64. Which is why whenever we take an odd root, we can actually keep that negative because I'm multiplying it together an odd amount of times, so we can end up with a negative. So again, I'm going to combine to a single parentheses and exponent. So my answer here would be negative 4x to the third. Okay? So now let's look at one last type of problem that we might run into. So notice here we have 64x to the 6th. Well, hopefully we can kind of see. Again, we're dealing with a square root, so we want to rewrite things to exponents of 2. And so we know that 64 is x squared. And then x to the 6th. Again, we're looking for two things that multiply together to give us 6. So that would be 2 and 3. We want the 2 to be on the outside. Again, now that they both have the same exponent, we can rewrite as all to a power of 2. And we're left with 8x to the third. Now, technically, that's the right answer as far as I have an 8 and I have an x to the third. However, let's recall back to our beginning of the lesson where I said when we're dealing with even roots, we always want to give our answer as the principal root, which is going to be the positive root. And the reason for that is because remember, if I have an even root, if I'm dealing with the real numbers, there's no way for me to have an even root and end up with a negative answer. Because if I had a negative number underneath there, then that would make it an imaginary number. But because, notice, I have a variable in this, I can't tell you if x to the third is going to be positive or negative. Because I don't know what I'm plugging in for x yet. So we have to make sure that it's going to be positive. And the way that we do that is by putting absolute values around our variable. Now you could include the 8 in the absolute values if you wanted to, but I already know the sign of 8, it's positive, so I don't have to, but it's not incorrect to do it. Now some of you might be asking, why did we not include it in any of the other ones? Well, notice in part D, I didn't end up with an answer. In part C, I had an odd root, and odd roots can be negative, so we didn't need to worry about it. And then notice that for part A and part B, they give us a specific sign that they wanted us to use, either the plus or the minus or the negative. In this case, they don't give us a sign on the outside, so we always assume that we want the principal root or the positive root. So that's why we have to add the absolute values. Now, on our next one, it's going to be very similar. The only difference here, though, is that we have a fourth root, which is fine. So again, kind of thinking through my numbers, well, 2 to the 4th is going to be 16. 3 to the 4th, well, that gives me 81. So I want to rewrite this as 3 to the 4th, again, because I'm wanting to write my inside all two exponents that are the same as my index, which is 4 in this case. Again, now I want to think about two things that multiply together to give me 12, and I want one of them to be 4, so that would be 3 and 4. Again, remember that we want to put that 4 on the outside, and then hopefully we notice that to get our 16 exponent for our b, we would have 4 times 4. Now that they all have the same exponent, we can rewrite them as a single parentheses, and we get that that's to the 4th power. So now, just like before, they're going to reduce, so my 4th power reduces with my 4th exponent, and now we have 3a cubed b to the 4th. So we had an even root of 4. So again, we need to make sure that we're dealing with our principal root. So I'm going to put absolute values. Now, I'm okay if you just put absolute values around all of your variables, okay? But if we're checking our answers in the back of the book, or if you're looking at, other people's work, you might see it actually written as 3 absolute value of a cubed times b to the 4th. And the 3 and the b to the 4th are outside of our absolute value. And the reason for that is if we think about it, just like we know the sign of our 3, it has to be positive. Well, if something has an even exponent, like 4, I'm going to be multiplying that number together an even amount of times, which means that even if I plugged in a negative number for b, I would still end up with a positive answer. So I don't have to worry about putting the absolute value around the b to the 4th because it's already going to be positive. But like I said, including it in the absolute value isn't going to be wrong because the absolute value of a positive number is always going to be positive as well. So if you just want to include all of your answer in an absolute value, that's fine. The only thing to be careful about is if I had something like the 3rd root of a cubed, notice that we cannot put absolute values around that, because if it is negative, then our answer would be negative as well. So we can only add the absolute values, and we only need to add the absolute values when we're dealing with odd, or when we're dealing with even roots. We don't want to include them when we're dealing with odd roots.